Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course on control systems. So in the previous lecture we have seen how we can model mechanical systems which contain mass, spring and dashpot in general. So this is part of our endeavor at capturing this modeling aspect of physical dynamical systems. We first started with systems that we are likely to be most familiar with, which are electrical circuits, both passive and active, comprising op amps. And then we moved on to mechanical systems. Continuing along the same route, today we shall look at rotational mechanical systems, and we will see that they are very similar to the translational mechanical systems that we have seen thus far, only subtle differences here and there. The rotation replaces translation in this case, so the variables get changed accordingly. So without further ado, let me just draw the elements that go into the making of a rotational mechanical system and how their individual dynamics are characterized by. So the first element that you have is a rotational spring. So of course the symbol looks very similar to a translational spring, and also we also depict the stiffness of the spring by K. However, you see this is a different spring in the physical world, as it were, in the sense that it will be like a toroidal spring which opposes rotation, right. So either you rotate the object clockwise or anti-clockwise, the spring is going to resist your action, okay. So essentially if you are applying a torque, here is how the equation can be written. So the applied torque is balanced by the stiffness of the torsional spring times the angle by which you have rotated the spring. Okay. So you see immediately the similarity is that displacement is replaced by angle, right. So that is the first element. So you apply a torque like this, and this is what the result is. By the same token, you can also have a rotational dashpot. Again, the symbol is deceptively similar to that of the translational dashpot. However, here if you apply a torque, then the torque is balanced by, so this is the constant of the dashpot, right. So maybe I'll not use B here, let me use D here, right. So D is the constant of this dashpot which characterizes this dashpot, and it is proportional to theta dot, which is the angular velocity. So the translational velocity gets replaced by the angular velocity, right. And finally, instead of a mass, here you have something called an inertia, okay. So something that rotates like this, sort of a cylindrical object, that is the representation of this, right. So suppose you apply a torque here, the equation is given by, this applied torque is balanced by J, which is the moment of inertia of this block, times theta double dot, which is the angular acceleration, all right. Keeping these in mind, it turns out that writing down the equations of a rotational system are not really very different from the ones we have already seen, which are translational mechanical systems. So an example would serve the purpose perfectly. So let me take an example. So suppose you have a connection such as this is a shaft on which you are applying a torque, all right. Let us say this is an inertia block here which rotates, all right, and this is connected to an assembly of a parallel torsional spring and a dashpot such as this, of course a torsional dashpot. Let us say this is equal to 1, this d is also equal to 1, okay. Not just this, but suppose you have another one such as this here. In one go with this example, we will see how the circuit analogies can also help us in this, right. Okay. So let us say K2 is also equal to 1 and this dashpot which is D2, that is also equal to 1, and finally it is connected to the datum, right. Okay. Now suppose someone has told you that this is theta 2, the rotation theta 2, all right, and this is of course the rotation theta 1. And of course, let me say this j is also equal to unity. So everything is normalized. We are not really interested so much in the values as in how to tackle this problem per se, right. Okay. So now given that this is the situation, you might wonder how are you going to write down the equation of this, right. So here is how. Just like we dealt with electrical circuits, just like we dealt with mechanical systems, we will do the same thing here. So consider this part of the assembly here, this inertia block, yeah. Just like in a translational system, the mass decided, yeah, where you wrote your equations. Here this inertia block gets to decide what you are going to write the equations about. We will shortly see that that is not quite always true, but yeah, we will get to that when we get there. So what can we write this as? So the applied torque here, if you look at this portion, is balanced by what? Of course, there is this j, so it is j times s squared. Again, I am writing directly in the Laplace domain because you know that this is, so if you translate this to its equivalent, then this is what it is, s squared j theta s, right. This is the transform domain equation. So we are going to directly write in the transform domain here itself. So you apply this torque here, it is balanced, this is pseudo rotation, like we had a pseudo force. So it is got to be balanced. If you want to bring this to static equilibrium, it has got to be balanced by this js squared. What else is there? What is the net rotation of this spring and this dashpot? See, on the left hand side of the spring and dashpot assembly is a rotation of theta 1, on the right hand side is a rotation of theta 2. So the net rotation is theta 1 minus theta 2, right. So let me just write that down. So we have k1 times theta 1 minus theta 2. What is the relative angular velocity? Theta 1 dot minus theta 2 dot, is it not? So therefore we write this as theta 1, okay, let me not use the hybrid notation here, sorry, let me use the Laplace domain equations itself. So there is no dot here, we are replacing the dots with ss, right. So theta 1, again I am dropping the s in the argument of theta for brevity, right. So this is my equation number 1, but that is not enough. I have to get more equations because there are more variables. You see, you have theta 1 and theta 2, and my goal is obtain the transfer function between theta 2 of s and the applied torque, okay. So where can I write my second equation indeed? Well, it turns out I can just split it up here. So look at this segment here, right. So what is my second equation? You see, if I write the equation for this segment, there is no externally applied torque here. If I have decided to cut the connection here, there is no externally applied torque here, so I easily write a 0 on the left hand side. But what about the equation on the right hand side? What is balancing this after all? What is on the left of this? On the left of this is what I have given by theta 2 minus theta 1, which is arising due to this. So this is k1, right, plus d1s theta 2 minus theta 1, right. So that is on the left hand side, plus on the right hand side this spring and this dashpot experiences a rotation of exactly theta 2 and only theta 2, because this is connected to the datum. So whatever is the net rotation here is actually the total rotation with respect to the datum, right. This theta 1 is the total rotation of this point with respect to the datum. Therefore, the net rotation of this spring and dashpot is theta 1 minus theta 2. I want you to notice that this is exactly like the voltage equations, and that is why, like we had displacement or velocity being analogous to the voltage here, here also we will have the angular velocity being analogous to the voltage in an electrical circuit, right. Okay. What is this being equaled by? This is nothing but k2 times theta 2 plus d2s times theta 2. Okay. So let me explain that equation a bit. Okay. Of course, I told you that there is no externally applied force here, or a torque here rather. Now instead what you could have written was, you could have actually taken this, you could have taken the sum of this term and this term, which is k1 times theta 2 minus theta 1 plus d1s times theta 2 minus theta 1, right. You could have taken these two terms and pushed them to the left hand side of this equation number 2. Yeah, of course they would have carried a minus sign, but if you adjusted them, then here's what you would have got. You could have written them as k1 times theta 1 minus theta 2 plus s d1 times theta 1 minus theta 2, which is balanced by k2 theta 2 plus d2s theta 2. Now this looks more like a balancing equation, you see. Why am I saying that? If you split this up along this red dotted line that I have shown here, then you see on the left hand side, what is the net effect, right. So the left hand side has the torque exerted by this assembly, right, and on the right hand side that is balanced by this assembly. There is no inertia block here. So when I said that inertia blocks get to decide where you are writing your equations, that is not exactly always true. Here you do not have any inertia block in between, but still you knew how to split it up here. Of course, we will shortly see another method of solving this which will dispel all our doubts. Nevertheless, you notice that whichever approach you take, I can call this equation number 2a, right. Whichever approach you take, this is the same equation. Either you split it up here and you equate the externally applied torque to be 0 and then balance it here, or you look at the net applied torque by this assembly, which is this on the left hand side of this equation, and that is to be balanced by this second assembly here, right. So now if we try to write down these equations, you can just take it out as an exercise, because I have normalized everything. Calculations become pretty simple. These are all 1, right. So calculations become pretty straightforward and simple. So if I normalize this, what I am eventually going to get is, you can take this as an exercise to complete this, gs is equal to theta 2s upon ts. I worked it out, so I know the answer. It's going to be 2s squared plus s plus 1. So what you have to do is, again, you can apply Kramer's rule, or you can simply substitute, because this part of the equation has 0 on the right hand side. So you can take all the terms related to theta 1 on one side, all the terms related to theta 2 on the other side, and get the relation between theta 1 and theta 2, and substitute for theta 1 in equation number 1, all right. And then everything gets on the right hand side gets to be written in terms of theta 2 alone. So you club it together and you get the ratio of theta 2 over t, right. So this is going to be the transfer function. Now you might say, well, I am not very happy with this method of solving this, and yeah, I understand that you might be a little uncomfortable. How do I arbitrarily break this down? Suppose you have more such assemblies without any inertia block, you have more such assemblies. So are you going to just split up at every such juncture and write down all those many equations? Yeah, doesn't seem very efficient, right. So is there another way, I wonder, right. So just like if you don't have voltage sources in an electrical circuit, if you have a single voltage source and multiple loops, you could as well have reduced it to a series parallel equivalent and gotten it down to a single loop. Here also you have just one inertia block, right. So I wonder if I could have just reduced this remaining part of the circuitry. Of course, by circuitry I mean the rotational mechanical systems elements here, not an electrical circuit, right. So I wonder if I can reduce these blocks And if you recall from our previous lecture, we've already seen how to reduce these blocks. You see, if you treat these terms like impedances or admittances, when they are in parallel, you can simply add them, because we've seen that the parallel equivalent is closer to the physical reality, right? So these are then like admittances. So you can add these two, and when they're in series, then you get to add their reciprocals and you get the equivalent reciprocal, right? So let us try and do that. So what about the first block here? Let's just look at this 1. So I'm now just going to replace it by its transformed equivalent. This is S. There's the first block, and then you have the second block, which is also a 1, and then you have this dashpot, which is again an S, right? So you are interested in the theta 2 at this juncture. But for the moment, let us try and club this together and try and reduce this. Yeah. So I wonder, what is this equation going to look like in such a situation? And that is going to be, we shall see that that's going to actually simplify or make life a lot simpler for us, right? So what about the equivalent admittance of this block? Remember, theta, or rather S times theta, is basically like the voltage, and torque is like the current. So basically you have a current source, which is the applied torque. Of course there's this inertia block here which we haven't drawn here, right? So it's this torque that's going to act like a current source, right? So the voltage drop can be given by, V across this, which is basically theta 1 minus theta 2. So the voltage drop across this, of course S times theta 1 minus theta 2 to be precise, but we'll get there shortly. Right now we are just interested in this, right? So theta 1 minus theta 2 is the net torsion across, or net rotation across this block. So what are we going to write this down as? So can we not reduce this equivalent as S plus 1, right? In other words, we have S plus 1 times theta 1 minus theta 2, right? That is going to equal the torque, because remember the torque is like the through variable, the current. That's our first equation. And the second equation, again the same torque is being transmitted here, so we can write the same torque as S plus 1 times, this time this is just going to be theta 2, right? So now from these equations, it's easy to see that you have theta 1 minus theta 2 is equal to theta 2, or in other words, you have twice theta 2 is equal to theta 1. Yeah, this is an important thing to remember. Why is it important? Because now we are going to reduce this entire block into a single unit. How are you going to do that? Think of the series parallel equivalent. So what is the admittance? The admittance of this block is S plus 1. The admittance of this block is S plus 1. So what is the overall admittance of these two blocks? The overall admittance, so this is Y1 is equal to this, Y2 is equal to this. So the overall admittance Y is going to be nothing but Y1, Y2 upon Y1 plus Y2. It's just like series admittances, yeah, Y series, because these two blocks are in series. So we get to write that as S plus 1 times S plus 1 upon S plus 1 plus S plus 1, which is going to be nothing but S plus 1 upon 2, right? So these are all my rough calculations. So this is going to be my second observation here. So remember, what I am going to do now here is, instead of writing those two separate equations and deciding at every juncture I am going to write a different equation, I am going to just reduce these blocks, just like when you have a, just to give you the analogy, when you have a single voltage source like this, and let's say you just want to find the current through, you want to find out the total current through this, that's flowing through this circuit, right? So what do? Instead of writing these two loop equations, you might as well take this impedance or this admittance as Z1. Let's take this impedance as Z1 and take this impedance as Z2, and then what you do is you take Z1, Z2 upon Z1 plus Z2 as equivalent, plus let's call this Z3, Z3, right? So instead of taking loop equations, this is what you do to reduce your effort. This is the Z equivalent, and then you divide this voltage by this Z equivalent and you get your current, right? So here we are doing something very similar, only thing we are using current sources because that is closer to the physical world. We are keeping the through variables and the across variables intact with this notation, right. So now what do we have to do? So the next step is, therefore, if I have just reduced this entire block, so now I am left with only this this inertia block, this torque here, right, and let us say this is the equivalent y here, y equivalent. I do not know what is inside this, and this is the datum. Of course, I know from here I have already derived it is s plus 1 by 2. So this y equivalent, I mean when I say I do not know what is inside, I mean the physical construction, but this is the equivalent, the analytical equivalent construction. So this is s squared. So then what I can write is s squared, and let us say this is my theta 1. So s squared plus s plus 1 upon 2 theta 1 is equal to t. In other words, I can just write this as theta 1 by t is equal to 2 upon 2s squared plus s plus 1. But remember, I have to find, apparently the goal is to find theta 2 over t. So how do I do that? Because I have obtained theta 1 over t. Well, it is very simple. That is the reason why we derived this boxed condition here, right. So now I am going to just replace this here. What is theta 1? You are going to tell me that it is 2 theta 1, 2 theta 2 therefore, because theta 1 can be replaced by 2 theta 2 according to this boxed equation that I have derived, upon t is equal to 2 upon 2s squared plus s plus 1, which leads me to the conclusion that the required transfer function is nothing but 1 over 2s squared plus s plus 1. Again the same result like we obtained using those simultaneous equations. Yeah. So you see, when you do not have these inertia blocks, you might as well do the series parallel reduction, right, and then finally at this terminal you might find out the total current. Just like instead of this current, if you are asked to find the current through this, then you will be using the current dividing rule to find out what is the current flow through this and this, right, if you reduced it in the series parallel equivalent. So I want you to notice and take home from this discussion the point that there is a very strong analogy between the analysis of electrical circuits and those of these rotational systems. Of course, barring few exceptions like I pointed out in the previous lecture, there are these things called inerters, which are in the true sense the equivalents of inductors, right. So every mechanical system, be it rotational or translational, can be depicted by an equivalent electrical circuit, but not every electrical circuit can be always depicted by an equivalent mechanical system, because things like masses and inertia blocks are like single terminal devices, right. In other words, you cannot share mass between two loops, two independent loops all the time. Neither can you share the inertia blocks between two independent loops, because you see the terms that come associated with these inertia blocks or the masses are individual absolute terms, either theta 1 or theta 2 alone, but not theta 1 minus theta 2 double dot. Yeah. So that is a slight aberration, but apart from that, yeah, all the techniques that we have learned for electrical circuits, if we just know how to split them up and use them cleverly, we can actually solve for mechanical systems in the same vein, right. So having seen this, I hope that the idea of modeling rotational mechanical systems are also clear. We will now look at something which is particular to only rotational systems, which are gears, and I put it to you that these are actually the equivalents of what in electrical circuits appear as transformers, all right. So what is a gear? What is the job of this gear, you might wonder. So you might have encountered these gear systems in your real life. So for example, if there is a gear here which is coupled to a larger gear here, so let us say there is a shaft that is connected to this and there is another shaft that is connected to this, right. So then what happens is you might have a prime mover connected to this, which causes the rotation of this, let us say in this direction, in the clockwise direction. Then this will cause an anti-clockwise rotation in the bigger block, but the rotation will be considerably slowed down, because you see at this point the velocity is same. The translational velocity at this point is common to both the gears, which are connected or which are teethed together at this point, right. So this is basically the common linear velocity or translational velocity. Now of course, we know that v is equal to r omega. So if v is the same for both of these gears, but you have r1 omega 1 for the smaller gear, let us say, and v is equal to r2 omega 2 for the larger gear, right, then you see that immediately for the same v at this point, which is basically the translational speed of rotation of these two gears, that is common, the one with the smaller radius, yeah, will have to rotate faster. So omega 1 by omega 2 is equal to r2 by r1, right. And now therefore, it stands to reason that in a given time span, let us say delta t, the total angle rotated by gear 1, which is omega 1 times delta t divided by omega 2 times delta t, right. So this is basically theta 1 over theta 2. This is nothing but r2 by r1 again, because you know you can cancel out the delta t and delta t from above and below on this side, right. So this is r2 by r1, right. So that is the first important relation for a gear, right, because at this point they are tethered together. So this has a common velocity. What is the second important relation for a particular gear? Yeah, the second important relation is, of course, now we will say that from this n1 theta 1 is equal to n2 theta 2, where n is basically, this is the first side, this is the primary and the secondary side. So ni is equal to teeth. So this is the number of teeth on ith gear. So here the assumption is, and of course this is a reasonable and valid assumption, that the width of each individual tooth has to be the same irrespective of the size of the gear. Why? Because remember, if the width of the teeth were different, then once you fit in this gear with this gear in an assembly, this gear will only be unique to this assembly. If you want now replace this gear with a smaller gear or a larger gear on this side, then you will have to again replace the bigger gear too. So in standard manufacturing practice, it is a good practice to assume that or consider that the teeth of each gear is identical, right. The teeth width, individual teeth width of each gear is identical. It is a standard manufacturing practice. In that case, the one with the larger circumference will accommodate greater number of teeth. Why? Because remember, if you have n number of teeth, then n times the tooth width, n times the individual tooth width is equal to the total circumference. So we have that n is proportional to 2 pi r, right. So therefore n is also proportional to r. So now we can write that n1 by n2 is equal to r1 by r2, but we have already seen here r2 by r1 is equal to theta 1 by theta 2. So therefore this is nothing but equal to theta 2 by theta 1. So let me box this part now. Yeah, this is now an important equation. Okay, so we have seen how, based on the fact that this point shares a common velocity, we have this relation. Based on the fact that the number of teeth is proportional to the circumference and then in turn the radius, we have the second relation. Now in addition to this, based on the fact that just like a transformer has V1 I1 is equal to V2 I2 being the powers on the primary and the secondary side, and of course you can multiply it by T to equate the energy on either side. Similarly, for a gear, you will have T1 theta 1 is equal to T2 theta 2. This comes from conservation of energy. So if your gear is lossless, okay, so that is the assumption here. So if your gear is lossless, then you have T1 theta 1 is equal to T2 theta 2. So combining all of these terms together, we will see that this R1 by R2 is something that we want to get rid of. We do not want to bother with this. So combining, because we do not want to always count, these measures, whether the radius of the gear. We specify a gear by the teeth, because the tooth width uniquely specifies the radius. Yeah, the tooth width and the number of teeth on the gear uniquely specifies the radius. So we get rid of this. This is a redundant variable as it turns out, right. So therefore, now we have from this relation T1 by T2 is equal to theta 2 by theta 1, is equal to, from this what do we know, theta 2 by theta 1 is equal to n1 by n2, right, n1 by n2, the important relation that we are looking for. Okay. So this is what we should remember. Maybe let me box it by another different color here to highlight the importance. So once you have seen why this relation must be true based on our discussions here, the rest of it, it turns out, is going to be pretty simple. So how so? Again, let me take an example to clarify this. Okay. So suppose you have a torque being applied here, and this causes a rotation of theta 1 on this side, and then you have this gear here, alright. So you have this gear assembly. So let us say on this side you have n1 turns, on this side you have n2 turns, and then this another shaft here which is connected now to an inertia block of inertia J, and then let us say you have a torsional spring K and a torsional dashpot, say D, right, and this is the datum, alright. And now the question before you is to find out, yeah, so we want to find out this ratio, this transfer function from T1 to theta 1, right. So this is our goal. Okay. This is what we want to find out. So how do we go about this? Yeah, it might appear very cumbersome and complicated to begin with, but a moment's thought will tell you that it is not actually so. So why do I say that? So the first thing is, observe that when I reflect this torque from this side, this primary side to the secondary side, what is the transformation ratio? So what is the equivalent torque that is appearing on this side of the gear? Yeah, because there is nothing else on the primary side except for this torque. Let me just see what the equivalent torque on this side is. So this is going to be nothing but T1 times, basically I am using this relation, this part and this part, right, and I know that I am going from the N1 side to the N2 side, right. So what is going to be my torque applied on the other side of this, right? It is going to be nothing but N2 over N1, because this is T1, this is T2. So what is T2? T2 is going to be equal to, if you take T2 on this side, it is going to be T1 times N2 divided by N1. That is exactly what I have written here. And now I can totally forget about this part, because the only quantity that was appearing on this side was the torque, the externally applied torque, which I have already brought to this side. So now let me write down the equation on this side in the usual fashion, and it is very simple now. So T1 N2 over N1 is going to be nothing but J S squared plus, since these are in parallel, so let us call this, let us say theta 2, right, J S squared plus K plus ds times theta 2s. But remember, this will not suffice. I have got T1, that is good, but on the other side here I have theta 2, so I have to actually reflect, or rather substitute for theta 2 in terms of theta 1. How do I do that? Once again, this will help me. So what do I know about this? This is going to be nothing but Js squared plus ds plus k. Yeah, remember why this is coming as a sum? Because this is a parallel assembly. Yeah, so basically if this is theta 1 here, this inertia block is being rotated, sorry, by theta 2 here, if this inertia block is being rotated by theta 2, then with respect to the datum, both of these k and d are being rotated, the spring and this dashpot are being rotated by theta 2 itself, right. So that is why we have this equation, right. Now I want to replace this theta 1 in terms of theta 1. So I want to replace this theta 2, sorry, in terms of theta 1, and this relation will come in handy. So what is theta 2? Theta 2 is nothing but N1 by N2 times theta 1. So let me write N1 by N2 times theta 1, and I am done, because now I have got T1 on one side, I have got theta 1 on the other side. So if I want to write down the relation, here is what it will look like. Theta 1 over T1 is given by the relation which is N2 upon N1 in the numerator divided by we have n1 over n2 times js squared plus ds plus k. But I am not very happy with this sort of a clumsy writing. So, what I will do is I will write theta 1 by t1, and it turns out this is going to be nothing but 1 over, and this is important, j equivalent s squared plus d equivalent s plus k equivalent, where j equivalent is nothing but, notice, j1 times n1 by n2 squared. What have I done? I have basically brought down this n2 by n1 below, so obviously it gets to its reciprocal, which is n1 by n2. So then you have n1 by n2 squared, right? So each of these terms j, d and k, they get multiplied by n2 by n1 by n2 squared. So similarly you have k equivalent is equal to k times n1 by n2 squared, and then you have this d equivalent given by d times n1 by n2 squared, right. So this is very simple. So what have I done eventually with this expression? The result is, it's as if I am saying, if there is a gear assembly here, yeah, and you want to find out the terms, the transfer function between terms on this side of the gear assembly, then the way in which you can reflect these different blocks, there are only 3 different types of blocks: inertia, spring and dashpot that we have studied. So how do you reflect each one of them from one side to the other? Look at this. If this is my source side and I want to reflect it on this side, which is my destination side, then what I am doing is I am just multiplying by the gear ratio squared, where the gear ratio is defined by the number of turns on the destination side divided by the number of turns on the source side. So it is basically the destination divided by the source. So this is of course not the Laplace transformed S, let me write the big S, yeah. So destination by source squared, that is a quick way of remembering this, right. So if I want to reflect objects like inertia, spring, dashpot from one side of the gear assembly to another, all that I need to bear in mind is the gear ratio, the gear number of teeth on the destination side to the number of teeth on the source side, and then square it and multiply it with each of these individual blocks, and it is as if then I can forget about this gear assembly and I can just write this equation in this fashion, yeah. So that is how you account for this gear ratio, alright. So hopefully that sort of is a bit illuminating, and also we can heave a sort of sigh of relief at this relative ease with which we can deal with this gear assembly, because otherwise they appear to be pretty complicated objects in and of themselves, right. But this gives us hope that even when we have a complicated assembly, we can actually look at a simplified transfer function eventually by reflecting each of these components. So let us look at a quick example to elucidate this concept here and see how it helps us in solving problems. So you have a torque applied here, you have an inertia block here, suppose, and let us say this is connected to this dashpot. Again, everything here is a torsional dashpot. So these are all unit, again normalized, okay. Alright, and then we have this, which is a gear assembly. So the number of teeth on this side is 50, and the number of teeth on this side is, let us say, 100. So it is a 2:1 transformation on the gear ratio, right. And on this side, so now remember in the earlier case we had nothing on one side, yeah. On this case we have the spring appearing on one side. So again the spring, its constant is given by 4, and then this is connected eventually to the datum, alright. So how do we deal with this? And let us say this is theta 2, this is of course theta 1, and the goal is we have to find out the transfer function between theta 2 and t. How do we do this, right? So the first thing we do is, as we have seen here, let us just reflect this, let us get rid of this gear assembly. So let us just reflect this spring to the left hand side, to this side. So then we see that we will be left with an assembly like this, which is T here and then we have this inertia block here which is 1, then we have this which is the dash pot here which is again 1, let us say s, this is 1 times s squared, right. But now we are reflecting this, so what is the destination side? 50. What is the source side? 100. So what is going to be my transformation ratio? It's 50 by 100 squared times 4, which you can check is just unity. So when this spring gets reflected on this side, it carries with it a stiffness of unity, and now I have gotten rid of this. But here's a catch. Remember, I was asked to find out the transfer function with respect to this variable which appears on one side of the gear. But now this theta 2 that I shall see reflected out here is not the same as this theta 2, no? It's going to be, let's call it theta 2 hat. So this is going to be theta 2 hat, not the actual theta 2, right? This, however, still remains theta 1. So how we will get from theta 2 hat to theta 2, of course we have already seen it, but we will come to that later for this particular problem. Yeah, first let us just treat this theta hat and forget about the gear assembly for the time being. So what is going to be our equation then? So our first equation is, again, you know, these are blocks in series. So what can we do about these blocks here, right? So of course the first equation that we can write is, you have s squared theta 1, yeah, plus s theta 1 minus theta 2 hat, yeah. This is going to be equal to the applied torque, right. I am just thinking of this segment here, yeah. So I have just partitioned it here, okay. Again, you could have used the circuit equivalent. I am just writing the equations here. You can try that as an exercise, that reduce this to the equivalent circuit. So you will then see that this is like S, so this is admittance is 1 by S, and this one has 1, so you have 1 by S times 1 by 1 by S plus 1, yeah, that is going to be the equivalent admittance. So you can try that, take that as an exercise, yeah, and you will see you will come up with eventually the same result that we will get to using our equations here. What about the second case here? Yeah, for the second case we can now write, of course, what is the total twist or total torsion experienced by this dashpot? It is nothing but S times theta 1 minus theta 2 hat, which is balanced by the spring times theta 2 hat. So this is theta 2 hat. This is my second equation. So quickly what I am going to do is, from this second equation I am going to write down S theta 1 is equal to S plus 1 theta 2 hat, right. So let us call this 2a, and then I am going to just plug in this particular equation, right. So I want to get rid of this theta 1. So I can write this first equation, then 1 rewritten as, just replace this, S squared plus S theta 1 minus S theta 2 hat is equal to T. So you now replace this theta 1 in terms of theta 2, so you get S squared plus S, sorry, this is S squared plus S, S squared plus S times, what is theta 1 in terms of theta 2, times S plus 1 by S theta 2 hat minus S theta 2 hat is equal to T, right. So again I can pull out this S common and it cancels with this S. So you can easily see that this is S plus 1 whole squared minus S common with theta 2 hat is equal to T, which tells me that theta 2 hat over T is nothing but 1 over S squared plus S plus 1, right. But I am not done yet, yeah. I needed to find out the transfer function between theta 2 and T, and what I have found is the transfer function between theta 2 hat and T, which is nothing but the transformed angle across the gear. So what is the relation between theta 2 and theta 2 hat, right? Again I am going to make use of this golden ratio here, not the golden ratio as in phi, but of course this relation here. So if I want to reflect what is the relation between theta 2 and theta 2 hat, let me just, since there's a lot of white space, let me just use this part here. So what I can then write is, think of this assembly here. So theta 2 times, yeah, so this is theta 2. So look at this relation here. So I can write then that 100 times, again notice this, 100 times theta 2, 100 times theta 2 is equal to 50 times theta 2 hat. In other words, theta 2 is equal to half theta 2 hat, right. So let me then draw a line here. Therefore, theta 2 hat upon t is equal to twice theta 2 upon t, which I know to be equal to this g. Let us call this g. Therefore, theta 2 upon t is nothing but half g, which is going to be half divided by s squared plus s plus 1. So I urge you to check using this series parallel reduction method that you will come up with exactly the same transfer function as we have obtained using these equations here. Okay. So that brings us to the end of our discussion on rotational mechanical systems, but the next topic is going to be even more fascinating, and this is going to be the last example we are going to pick up in so far as modeling of systems are concerned. So of course we give it a big name, electromechanical systems, but essentially what we are going to look at is a DC motor. Okay. So we will see how this equation or this modeling of this DC motor is an armature controlled DC motor. So what we are essentially going to look at now is armature controlled DC motor, right. So what we are going to look at now under the guise of looking at an armature controlled DC motor is a combination of different types of systems. And the beautiful thing that will emerge here is, you see this level of abstraction that it allows us to do. How so? Look, once you have written down these equations and these variables mathematically, you can now forget about the physical reality. Whether these are torques and angles or whether these are voltages and currents cease to matter. So that is the level of abstraction in this mathematical modeling. Okay. We shall see that now that we are equipped with all the tools to deal with electrical systems and mechanical systems separately, even including rotational mechanical systems with gears, we shall see how all of those fall into place here, and all of our knowledge that we have acquired through our discussions thus far will enable us to model an electromechanical system such as a DC motor, where on one side you will have some electrical equations, on the other side you will have some mechanical equations, then there will be some bridging equations which will be electromechanical equations, and combining all of these together, it might seem like apples and oranges. Yeah, on one hand you have torques, on one hand you have voltages, right. So these seem like incomparable variables, they come from different physical systems, different differential equations, but it is this beauty of this abstraction in mathematical modeling using this Laplace domain that will allow us to combine all of them together and perform just some algebraic operations instead of differential equations. Okay, so that is the beauty. A word to the wise, even though we might conclude on our discussions with our discussions on modeling of mathematical systems, mathematical modeling of physical systems with this, it is by no means a suggestion that this is all there is to mathematical modeling. The reason why in this course we are discussing mechanical, electrical and electromechanical systems is because of the audience's expected familiarity with these systems. Now as a control engineer, you cannot crib and complain about it when you are given a particular system about which you have no idea. It is the job of a control engineer to acquire domain knowledge. Yeah, here it is relatively easy because you already have domain knowledge about electrical, mechanical and electromechanical systems through your coursework, other subjects. But even if you are given a system which is an exotic system about which you have never read in your textbooks, it is your job as a control engineer to read up on it, to acquire domain knowledge. It could be a biological system, it could be a nuclear reactor, it could be any system, yeah, which you probably haven't learned within the purview of an electrical engineering or a mechanical engineering curriculum, but you cannot complain. You have to acquire domain knowledge, you have to take suitable assumptions, and you have to model it mathematically. Yeah, that is the job of a control engineer, right? So again, just to reiterate, this is by no means an exhaustive coverage of mathematical modeling, but hopefully this is one that will give you some idea about how to deal with modeling of physical dynamical systems. So without further ado, let me just describe this system before you and describe to you the principle, working principle. You are already aware of this, but just to refresh your memory, let me just draw the circuit and sort of rewind, recapitulate what you already know about electromechanical systems. And in the next lecture, we shall get into the detailed modeling and wind up with this modeling of an electromechanical systems, and then move on to other topics, analysis of dynamical systems. So here goes. So in a typical DC motor, you have an armature voltage, let's say it's VA, which is applied here. Yeah, you have some armature resistance, and you have some inductance here, right? And then here you have the armature across which there is a back EMF. So this is, let's say, VB. Okay, this is VB, to which you probably have a shaft connected, right? And across the other end of this gear assembly, you have your load connected, which is, let's say, this J of L, right? And let's say it's connected to the datum via a dashpot, like so. All right, so this is overall the assembly. Of course, there's a field circuit here. So in a field controlled DC machine, it is a field current that varies, which controls the flow of current through the armature in turn. All right, so this is basically the IF, the field current. Here we will assume that this is armature controlled. Armature controlled, hence IF is constant. Okay, so this is a field circuit. Of course, the field circuit has its own RF, resistance and inductance. Yeah, so maybe after we've covered this armature controlled DC motor, I leave the field controlled modeling as an exercise to you. Yeah, so you can try and model the field circuit. Okay, so let's call this the motor side gear teeth, and this is the load side number of teeth. All right. Yeah, so this is overall the assembly. This is how it looks. Okay, now suppose someone gives you this, and now you have to model this system. Okay, so you have to basically write down the physical equation. So you have to have a physical understanding of the system. As I said, any mathematical modeling involves domain knowledge about the physical environment of the system, right? What are the physical laws governing the system? Yeah, so it turns out that for this system we know each and every part, how the physics of the individual part is. What are the physical equations, the differential equations governing the dynamics of each individual part. So we should be able to write it down. So in the next lecture, which is coming up, we'll see how we write down these equations in the Laplace transform domain and eventually obtain. Remember, the goal here is to obtain the transfer function between this rotation of the motor, the angle rotated by the motor side of this shaft, to the armature voltage. So you are controlling this rotation of this side of the motor, this shaft, with the variation in the armature voltage. Okay, sometimes you can also control the speed, in which case it will be omega ms over VAS. But then these are not very different, because we know that omega ms is equal to nothing but s theta m s. So we will look at this modeling in the next lecture. Okay, for now this is some food for thought. Think about how you are going to approach this problem using your domain knowledge.